Hello everyone, my name is Okeoghene Jonathan Benjamin, and I'll be presenting on a review of grinding of silicon wafers. This project is part of the coursework for IE 5352 Advanced Manufacturing Systems in the Department of Industrial Engineering TTU. This paper is it's a dual project, so I'll be taking you through the first half of this presentation while my partner takes you to the conclude. The topics covered in this presentation include the introduction to grinding, the study scope, grinding of silicon wafers, grinding wheels and materials, the 3D printing of grinding wheels, ultra thin and ultra precision wafer grinding, the grinding fluids, and finally, the conclusion. I will cover the first 8 sections while my partner will discuss the rest. Grinding is a widely used but complex machining process. Its primary purpose is to achieve material removal while ensuring a desired surface finish. The process significantly enhances surface integrity, dimensional tolerance, and form tolerance. Well, you can think of grinding as when you have a wood and then you're getting to the end of the final product, and then you have some waviness created in the previous process, and then you use sandpaper to like smoothing the surfaces, clear those waviness off the wood. This can also be called grinding, but in this case we're talking about integrated circuit manufacturing, so it's way more than that because we have to use tools for this. So interestingly, grinding can account for 20 to 30% of the total expenditure in machining operations, as reported by Mihik et al. In 2013. In the semiconductor industry, monocrystalline silicon wafers are the most widely used substrates in the IC manufacturing. Okay, they demand extremely high surface quality and flatness. And what grinding does is it helps improve surface damage and waviness caused by earlier processing stage, as highlighted by Pei et al. In 2018. And also, subsequent polishing then ensures damage-free wafer surface suitable for IC packaging. Like I said earlier, the use of sandpaper to clear off waviness off the log of wood when you're trying to make a furniture. Then the wood smoother is used. I don't know what it's called. A rasp or a planer is used to smoothen the surface. Okay. Then we use the painting, like spraying, to polish the entire surface for more smoothness. So the grinding process in that log of wood being transformed into a furniture will be the sandpaper process. Okay. Study scope. This study involves an extensive literature review using platforms like Google Scholar, Science Direct, Springer, and IEEE. We focused on peer-reviewed papers published between 2009 and 2024. In total, we reviewed about 40 papers covering key topics like silicon wafer grinding, the grinding wheels and materials, 3D printing of the grinding wheels, ultra thin and ultra precision wafer grinding, grinding fluids, and the effects of the grain size. Well, after reviewing several papers, we narrowed our search down to materials used for grinding, like the grinding wheels and the materials and how they affect the substrate. Well, monocrystalline silicon wafers require both high surface quality and flatness to meet the stringent demands of IC manufacturing, considering the fact that everyday IC chips become smaller and smaller, and as it becomes smaller, it becomes flatter. So we're trying to observe what's going on between these years. Okay, so the grinding process removes surface damages and waviness, preparing the wafers for subsequent polishing stage. This ensures that the wafers meet the IC packaging criteria as observed by Pei et al. And Tiomate. There are four main types of abrasives used in grinding. We have the silicon carbide, the aluminum oxide, the cubic boron nitride, most times called CBN for short, and diamond, of course. So for silicon wafer grinding, diamond and CBN are preferred because of their high wear resistance and thermal conductivity. Right to my right, you would see an image that illustrates the surface quality achievable with an 8,000 diamond wheel. So diamond grinding wheels, for instance, they offer exceptional hardness and low frictions, while CBN, that's cubic boron nitride, they provide better thermochemical stability, making it ideal for specific applications. Okay, so we have images here which illustrates how the CBN and the diamond wheel looks like from the references Kengol, Keng et al. And from Kufia et al. In 2017. Silicon grinding uses different types of grinders, okay? Each with its own unique property and purpose, okay? So for the first, we have the Blanca type wafer grinder, and this is like it's a very quick and dirty option, okay? So it's very great for removing large amounts of material very quickly. And when something is very quick, it might not be as effective as a slower approach. Well, then we have the in-feed grinder. This is very perfect for precision, and precision is key in IC manufacturing. So it is very very precise. Okay, it is perfect for precision, such as grinding the edges of a wafer to a specific dimension. And lastly, we have the simultaneous double side grinder, the SDSG. Well, this is like a multitasker. It grinds both sides of the wafer at the same time, ensuring uniformity. Okay, so the SDSG is mostly or often used by manufacturers that need to produce like high volume of wafers with consistent flatness, such as like mass production. The As we had in the class, the example of the Apple A17 Bionic chip, when you need to produce something as mass as that for mass production, rather, you would need to use the SDSG. Another example would be like baking two pizzas at the same time. Now you save time from baking the same pizza. You bake two pizzas at the same time. You save time, and both will be evenly cooked. So this is a very great example. From here on, my partner will take up the next slide till the end. Thank you.
Hi, my name is Kelvin Apesegah, and I'll be continuing the presentation from this slide onwards. Um, we'll be talking we'll be talking about wheel dressing or truing. These processes are essential for keeping grinding wheels in top shape. Dressing is like cleaning the wheel. It removes debris and worn-out grains so that the wheel can cut efficiently. And truing, on the other hand, restores the wheel's shape, which is important for precision and improves precision and accuracy. And laser technologies are basically changing the game. Unlike traditional mechanical methods, lasers offer non-contact processing, making the whole process much more precise and efficient. Right. And now we are going on to 3D printing of grinding wheels. And using additive manufacturing, we can now create wheels with complex shapes and internal coolant channels. This matters because these features improve cooling efficiently and make the wheels last longer. Imagine grinding wheels that can like deliver coolant exactly where you need it to be. It's like giving your grinding process like an extra edge. I guess like yeah, like an extra edge. Now moving on to ultra precision and ultra thin wafers. Now onto ultra precision and ultra thin wafers. In the semiconductor world, wafer thickness and surface precision are everything. With ultra precision grinding, we can achieve machining accuracy down to 0.1 nanometers and surface roughness below 10 nanometers. That's thinner than a strand of hair, I think. This is made possible using metal bonded super abrasive wheels, which are strong, wear resistant, and can hold their shape during intense grinding. Now we're moving on to grain size. It might sound small, but it's a very big deal. Finer grain sizes like 3 to 6 microns are preferred for back grinding silicon wafers because smaller grains means smoother surfaces and less subsurface damage. Coarser grit, coarser grit removes material quickly but leaves scratches, while finer grit gives a polished finish. That same idea is what's applied here. And yeah, moving on to ultrasonic assisted grinding, which is also known as rotary ultrasonic machining. Here's how it works. We take a traditional grinding machine and integrate an ultrasonic system. This setup reduces grinding forces and improves the surface quality of hard brittle material. It's like adding like a gentle yet effective vibration to your grinding process, which also makes it more efficient and precise, right? And moving on to surface grinding. Surface grinding plays like a very key role in wafer production in the sense that it's used at three main stages, which is after wire sawing to smooth the slices, after etching as a partial replacement for rough polishing, and during back grinding to thin wafers. The best part about this process is fine grinding after etching not only improves flatness, but also reduces the material removal required during polishing by 25 to 50%. That's a very important efficiency boost. And moving on to grinding fluids. These are like the least like the unsung heroes of the grinding process because they ease friction, they reduce heat, and prevents thermal damage to wafers. Today we are seeing very exciting innovations like environmentally friendly water-based coolants and cryogenic cooling with liquid nitrogen. These methods improve performance but also align with green manufacturing trends, which is very good for the environment. And to wrap things up, we covered a lot of ground. Ultrasonic technologies are making grinding more efficient, while advancements in grinding wheels are improving surface quality and the lifespan. But certain challenges remain, especially in achieving consistent wafer strength and finish. But the good news is research in this field is still ongoing, it's still going strong, and there's plenty of room for innovation. So yeah, if we keep pushing, the boundaries are the sky is the limit. There, we can keep pushing the boundaries of what's possible. Thank you.